Hi guys, welcome back. I'm here with the continuation of the part 1. So in the previous part we have studied how to calculate the quantity of seepage, that is one of the property of the uses of flow net, and in this session I'm going to explain the second concept, the uses of flow net, that is calculation of seepage pressure using flow net, which is very important. For that I'll just draw you a figure. As usual, this is flow line and equipotential line. Yeah, so calculation of seepage pressure at a point. I will just consider this point. At this point I need to calculate the seepage pressure. So what is the seepage pressure at this point? So how to find the seepage pressure at this point is the first formula, seepage PS. Seepage pressure at a point is equal to unit weight of the water into H. Of course, you know what is unit weight of water. The thing comes into play is what is H. H is hydraulic potential or balanced hydraulic head available after n potential drops. See, there are many potential drops which is going to happen. As far as we have studied in the previous thing, there will be a potential drop between the equipotential lines. The potential drops will be same. So at this point, so what is the n number of potential drops comes into play? That is, this small h will be equal to h minus n into delta h. So what is h? H is nothing but, if this is the level of water in the upstream side and if this is the level of the water in the downstream side, let me take this as H1 and this as H2, and this would become the difference in head. Okay, difference in head between the upstream and downstream will be your H, that is equal to H1 minus H2. This I had already explained. That is how you are going to find the value of H. Then what is the number? Okay, number into delta H. Delta H is nothing but head drop through the field. So of course in every field head drops takes place. If I want to find the seepage pressure at this point, I need to calculate the numbers. Okay, let this be 1, 2, 3, 4. In this case the number of potential drops that is taking place here will be 4, that is n. Then how to find the value of delta H is very important. Delta H is nothing but head drop through the field. A drop through the field can be found which is equal to capital H, that is, this is the capital H divided by ND. ND is nothing but number of potential drops. This is how, just by making use of this formula, you are going to find the value of seepage pressure at a point. Okay, this is how you have to analyze the situation. Next, let me move into the next concept. Calculation of this is the third use of flow net, that is calculation of uplift pressure from the flow net. How you are going to, so now you came to know what is flow net. That is how you are going to find the uplift pressure, that is in the flow net. The flow net, how the uplift pressure going to takes place. Uplift pressure can be found by keeping the piezometers, right? Okay, just by making use of the simple formula we can find the uplift pressure from the flow net, that is PU will be represented as uplift pressure, which is again equal to unit weight of water into HW. So what is HW? HW is equal to pressure head at the depth. Okay, at that point, at that depth, you are going to find the pressure head. Pressure head, how will you find the pressure head? Which is equal to total head at that point minus elevation head. That is, the total head will be capital H and the elevation head will be small h. Okay, this will be much clearer when you are going to solve the problem. Fine. Then the fourth use of the flow net, that is exit gradient. How would you like to find the exit gradient? Exit gradient is very important. I'll explain once again. If you take this as a dam section, the seepage is going to take place in this manner, flow lines and equipotential lines. Fine. So this exit gradient what you are going to give here is the very much important thing, because hence from the upstream side the water enter in this direction and get exited in this direction. The pressure of the water will be more here, and the toe of the dam, so this portion is called as heel of the dam and this portion is called as toe of the dam. The toe of the dam get deteriorated due to creation of pressure at this point. That is the reason you are going to give the exit gradient. So what is the formula? I exit is equal to delta H by delta L. Delta H is head drop per field. Okay, for every field there will be head drop, and we have also studied the head drop from channel to channel, it will be constant, which is one of the properties of the flow net. Okay, that is delta H per field. Delta L is the average length of the last field at the exit point. So you can see this is the last field. Okay, for this last field you are supposed to take the average length, and later on you are supposed to find the factor of safety. Factor of safety is equal to I critical divided by I exit, and by taking the safety features we need to calculate the value of factor of safety. If the factor of safety is not given properly, then there will be a action of piping. So in order to avoid the piping actions, we have to give the proper exit gradient that will be cross-checked with the factor of safety. Next, phreatic line. Phreatic line is very important. For that, I'll just draw you one figure. So, from bottom of the dam, flow lines, equipotential lines, and since there is a presence of water here like this, okay, there will be a seepage that is going to take place in the dam section, that is in this direction. Okay, so the seepage will be present only up to this point. Okay, in this point there will be no moisture. Okay, so I'll just tell you, phreatic line, it is also called seepage line or top flow line. Okay, this line, this is the top flow line, is called as phreatic line. There are many flow lines you can see here. Okay, the top flow line is called as phreatic line. Why it is called as phreatic line? Because along phreatic line the pressure head is zero, because upon this phreatic line there is no pressure at all, because the only moisture content is present here, and the dam will completely be dry above the phreatic line. Okay, that is the reason we can say the pressure head is completely zero on the phreatic line. Then this is MCQ point. Please remember, the shape of the phreatic line will be parabolic. Above the phreatic line there will be no moisture, and upon the phreatic line pressure head is zero. Cozy solution is also used to find out the seepage through the dams. That is one add-up point. Discharge to the body of the dam. Okay, body of the dam, there is some of the discharge that is taking place. That discharge can be calculated by Q is equal to K into S. K is, of course, you know, permeability, and S is the focal distance between the focus and the directrix of the parabola shaped phreatic line. So the most important thing that you need to find, that you need to remember here, is what is phreatic line. Phreatic line is nothing but the topmost flow line in the dam structure. The second thing, the shape of the phreatic line is parabola. What I am telling all these things is MCQ points. Then you can also find the quantity of seepage that is taking place through the dam. And one more thing you need to remember is, along the phreatic line the pressure head is zero, only atmospheric pressure exits above the phreatic line. Up to here the pressure will be there. Upon this point which I had marked in yellow here, there will be no pressure of water, there will be no moisture content, only water pressure will be exerted up to phreatic line. That you need to remember. Fine. So you can see here in this, This is phreatic line. You can see these are the flow lines and these are the equipotential lines, and above the phreatic line the dam is not subjected to the moisture or water pressure. The only above the phreatic line you can there will be atmospheric pressure, that's all. So you need to concentrate more on the upstream side in these things. And we have given the drainage system here. The water which is getting percolated into the dam is being drained by this drainage system. There are some literal specifications for this drainage system that I am going to explain it in the upcoming slide. So if I take the overall, I'll just revise you what are all the things that we have studied. Okay, this is upstream side of the dam, this is downstream side of the dam. So this height is, let me take it as h1, and if the water here, let me take it as the h2, and this is head causing flow, that is capital H. Okay, capital H is equal to h1 minus h2. Okay, this is the head difference between the upstream and downstream side, which is represented in terms of H. That is first thing. Second thing we had studied here is flow lines. So what is meant by flow lines? Flow line is a path traced by the individual water particle. Okay, this is first path, second path, third path. Okay, only in these paths the water is going to seepage, the water is going to percolate into the soil. Okay, so there will be some of the paths that I am going, there may be 1 2 3 4 5, there will be many paths though, but those paths is represented by which the individual water particle is going to flow. Then I am going to draw the equipotential lines. Equipotential lines are drawn in such a way that the individual equipotential line will have a same head of water wherever you stay. By keeping the piezometer, wherever you see in the equipotential line, the head causing flow will be same. Then the head difference, the difference in head from equipotential line to equipotential line will be constant. If the delta H is equal to 2 centimeter or 20 centimeter here, from this to this will be 20 centimeter, there will be equal potential drops. So this is all about and this is field. The shape of the field is square, that we have studied later on. So the topmost point, then in the same way the water which is present here is going to percolate into the dam structure also. The topmost line which is drawn, which is called as phreatic line. Shape of the phreatic line is parabola. Whatever I am revising here, it is very important in the MCQ's point of view. And upon the phreatic line, the pressure head up to here at the phreatic line, the pressure head of the water will be 0. Above the phreatic line, there will be only atmospheric pressure. There won't be any water pressure, and the moisture content of the moisture will be 0 about that point. So this is all about the basic elementary things. After this, let us study. Let us solve some of the MCQs. Let me see. One more concept, let me explain you. Seepage in anisotropic soil. So what is the difference between isotropic soil and anisotropic soil? In case of isotropic soil, the properties of the soil in the perpendicular direction, it will be same. In anisotropic, it won't be same. So in case of anisotropic soils, the value of K, how we are going to find the value of K? Value of K is equal to root of Kx and Kx into Ky. Kx is permeability of the soil in the x direction, permeability of the soil in y direction. That happens in case of anisotropic soils. Flow lines and equipotential line get deflected at the interface between the two dissimilar soils when they pass from one soil to another soil, because in anisotropic soil the similar kind of soil will not be present. For that, tan theta 1 is equal to K1 by K2. We can make use of this formula to find the thing. So this is all about the concept. In the next session, I am going to solve some of the MCQs, which is very important. Okay, thank you guys. If any queries, Please do comment in the comment section. I will help you by replying through your comment section, and please tell what are the things that need to be improved and what are all the concepts that you want. I'll come with those lessons, those concepts, everything. You please do comment me in the comment section. Thank you one and all. Bye bye. Meet you in the next session.